Hello,
Yeah, yeah.
hello.
Hello. We'll start after 2 minutes if no one joins.
Sir, will this class will continue till the gate 2023?
No, no, no. It will. I think after that two class will be there.
Next,
Next two class
after
will be there. After
after the two,
yes, after
after two next after 2 weeks, what
it will
happens? That will be closed.
it it will stop. We will stop. But they can plan something. I think new batch for new again. They will start again. I think.
Oh, oh, oh. Okay.
But I think
Thank you.
we have solved all the questions
Yes, yes,
almost.
yes.
Yes. Today we're going to solve three questions from GATE 2014 and then we'll solve some NMR question. So, hi everyone. First read and try to predict the answer, then we'll solve. The current order of rate of solubilities for the following chlorides in acetic acid is. Can you know solubilities which type of reaction? Substitution.
Substitution.
Which type of substitution? SN1, SN2, SNI, SN2 prime.
SN1.
Okay, SN1. So SN1 rate depends on what?
Only nucleophiles.
No, not nucleophile. For the living group only. Living group, I mean substrate, not depends on the nucleophile. It depends on the R. Some living group is there, so that substrate it will depend, not depends on the nucleophile. That's why SN1 only one substrate dependent. It depends only on this substrate. I mean 1, 2, and 3, not on the based on the acetic acid. So now predict which is the correct answer. I mean SN1 reaction will be fast. How fast the carbocation will form? I mean when the carbocation will form fast. If the carbocation is stable. So which carbocation is stable? Any answer?
B.
Then solve this one. Now we're going to discuss one gate question from gate 2014, question number 20. The correct order of the rate of solvolysis for the following chlorides in acetic acid is, so in the 1, 2 and 3 all are 8-member ring system and the chlorine is there, and in the option 2 and 3 the oxygen is placed in defined position, and we have to find out what is the rate of solvolysis reaction in acetic acid. So first come to the know what is solvolysis reaction. Solvolysis reaction is the one type of SN1 reaction. So what is SN1 reaction? So SN1 substitution unimolecular reaction. Okay. So in this reaction, the first step is the RDS. RDS means redetermining state, where the carbocation is formed and carbanion is formed. So if the carbocation is stable, our rate will be fast. If the carbocation is not stable, our rate will be slow. So from 1, 2 and 3, so when the chlorine will leave, so we have to find out which carbocation is more stable. So in this first form, in the first case, so it will form a carbocation like this. In the second case, it will form carbocation like this, and 1, 2, one oxygen should be there, right? And in the option 3, it will form carbocation here, and one oxygen should be there after 3 center. So here we observe in these two cases, 2 and 3, a long range participation, okay, due to stabilize this carbocation. But in this option 1, we cannot able to see any long range participation. So here what will happen? This oxygen lone pair will form a bond like this. So this carbocation will be now here. So this carbocation, like this type of stabilization will be there. Similarly, this type of also stabilization will be there. So that time carbocation will be here. Okay. So it will form 5, 5 member ring, whereas it will form 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4, 5, 6. 6, and this is 1, 2, 3, 4, 6, 4. So we all know that this is symmetrical and it should be more stable, 5, 5 than 6, 4. So 5, 5 member ring, 5, 5 ring will be more stable than 6, 4, and here no participation will be there. So we can say that 3 will react faster than 2 than 1. So our correct option will be option number B. So for more information, you can watch this NPTEL video. Thank you. Is it clear to everyone?
Yes, sir.
Yeah, then the next question. Hi everyone. It is very easy question. Just try to calculate the overall rate of the following reaction sequence.
83.3.
Now we're going to discuss one gate question from gate 2014, question number 24. The overall yield in percentage for the following reaction sequence is. So here is the three-step reaction. The first step the yield is 90%, in the second step 80%, and in the third step it is 80%. So we have to find it what is the overall yield. It has three steps. So to calculate that, first we have to write this formula. So the overall yield will be, so the overall yield will be in percentage. That will be, the formula should be like this. First write 90 because the first yield is 90%. Then whatever yield will be there after that, after n many step, just divided by 100. 80 by 100, answer into 80 by 100. Okay, so that will become 90 into 0.8 into 0.8. So if you multiply this, that will come 57.6%. Okay, so the overall yield will be 57.6%, but actually in real life it cannot be in fraction, so you have to it into the nearest integer. So nearest integer will be 50, 58. Okay, but in exam you can write 57.6%. So thank you.
Yeah.
Yes, sir.
Hi everyone, now I get
Think this question, then we solve. This is a very good question, I think. So the most suitable reagent combination to effect the following conversion is, so what they are doing, they are basically making the deoxygenation. They are making the OH group to hydride, replaced by hydride, right? So there are three functionalities there. One is OBM, one is OBZ, and one double one is there. So they are keeping intact this OBM, OBZ, and double bond, and they are doing only the oxygenation of the OH. So how can you do? So there are four options which will be the best option.
Option 1.
Okay,
It's maybe confused. Option 1.
okay. And what do you think the other option?
Hello.
What is the probable next option? I am not able to hear it.
Option C.
Okay. But in the option C, this butyrate cannot be act on silicon. Okay.
We're going to discuss one gate question from gate 2014, question number 25. The most suitable reagent combination to effect the following conversion is. So here is a OBZ group. This is six membering first of all with a double bond here. At, we can say this double bond here. One OBZ group, one ester group is there. One free hydroxy group is there, and one benzyl group is there. So both benzyl and benzoyl, both group are there, and what they have done, they have done the deoxygenation of this secondary hydroxy groups, keeping in intact OBZ and OBN, and in this double bond also. So we have to find out that which option is correct. So for that, so first option they have used is a sodium hydride, carbon disulfide, then methyl iodide, followed by Bu3SNH, that's tributyl tinhydride, AIBN, and benzene, followed by reflux. Second option is iodine PPS imidazole. Third option is hydrogen in 10% palladium carbon, acetic acid, and high pressure. The third option is trimethyl silyl chloride, pyridine, N-dimethyl aminopyridine, and option 2 is tributyl tinhydride, AIBN, benzene, and reflux. And option D is mesytyl chloride, pyridine, DMAP, lithium aluminum hydride, THF, and reflux. So we have to find out the which option is correct. So for that we have to first know what is the Barton-McCombie deoxygenation. In the Barton-McCombie deoxygenation, AIBN is used. The structure of AIBN is like this, where this radical cleavage is happening there. After that, this nitrogen gas will leave and we will get this. After that, there will be tributyl hydride from where they will take one hydrogen atom. So we will get from this Bu3SN radical. So after that, this Bu3SN radical will attack this xanthate ester. This bond will cleave. This so we'll from this we'll get this corresponding this compound and this radical. And this radical again acts up one hydride from this Bu3SNH and we get the deoxygenated product 6. So in the first option, when they are using sodium hydride, CH2 and methyl iodide, what will happen? So what will happen? So first step, there will be a formation of so OBZ, that is oxygen, OBN group is there. So OH. So in the sodium hydride, it will produce O minus, and there is carbon disulfide. So it will attack here, and this group will go. So what will get? You will get OBZ will be like this, and OBN also in same, and we will get O C double bond S, then S minus, right? After that, they are adding the methyl iodide. So what happened? This sulfur will S minus will attack here, one SN2 reaction will happen, and we'll get corresponding xanthate. So this is what xanthate. After that, again Barton-McCombie deoxygenation is happened. So this group will basically go and we will get the deoxygenated product. So option A is the correct. Now come to the why the option 2, B, C, D is not correct. Because this iodine is there, right? Iodine PPS. In presence of iodine, this double bond is basically iodinated. So we basically get a cyclic iodonium cation. So let's say it can be attacked from many sides. Let's say iodonium cation followed by one iodine will attack. So we'll get the diiodonium cation, like diiodine product. So that's why option 2 is not correct option. In the option C, when we treated with Me3SiCl, we'll get corresponding sterile protection of this Si. But after that, when we apply this condition, Bu3SNHAIBN, that condition only applies in xanthate, not this type of compound. So further the reaction will not proceed. So we will not get the product. In the option 3, acetyl chloride, pyridine, DMAP. When we try to use, so first step will be the methyl protection of this. So you get the OMS followed by, here we will get OBN, right? After that, when we try to use the lithium aluminum hydride, that time the methyl will also go. Simultaneously, this OBZ will convert to the corresponding hydroxyl group. So, in presence of lithium and aluminum hydride, this ester will also reduce and this O-methyl group is also go. The both reaction will go simultaneously, but the OBZ reaction will be much more faster than this deoxygenation. So that's why this option is also not correct. So our correct option should be option A. So for more information, you can watch this NPTEL video. Thank you.
This is clear?
Yes, sir. So can you explain the option number 4 again, sir?
Okay, just one. What is the what this is our substrate? Your OH group downside. So first is the methylation, right? You know the methylation is the methyl chloride. Methyl chloride. So first will be the OMS group. Pyridine is a base, so it will accept this OH group. I mean, it will not accept. It will just polarize the OH bond, and methyl chloride chloride will group and methyl is attached. And that DMAP is used basically. It has a non-nucleophilic base. Okay. So after that, when we use the lithium aluminum hydride is a lithium and 4 hydrogen is there. Okay. So this hydride can also attack here, and this group will goes out. So we get the corresponding alcohol. Because this center is much more electrophilic than this center, right? Because this is a keto group, right? So keto group is much more electrophilic than this deoxygenation. So hydride will also attack here, but very slowly. But this reaction will be fast. That's why you get the diol, some mixture of deoxygenated compound, and this group will remain intact. OBN. OBN is the basically OCH2 PH ether group. Clear now? Is it clear? Is it clear? Otherwise, I can explain again. I hope it is clear. Okay, then if it is clear, then we'll solve some NMR question. Solve this two. Option number two. Sorry, question number two. I hope it is visible. An organic compound with molecular formula C12H24O6 shows only one peak in one NMR as delta is equal to 3.69 and this singlet, and also one peak in 13C NMR at 70.7 ppm reduce the substructure. you people know how to calculate dB, double bond equivalent? What is double bond equivalent?
Yes, sir.
So what is the double bond equivalent in this case? First calculate that.
Six.
Not 6. So calculate double bond equivalent. Double bond equivalent dBE. Let's say CnHm. Double bond equivalent would be n plus 1 minus m by 2. Okay, this is for normal CnHm. So first do some example. Then what will be double bond equivalent of C8H10? Calculate first. So here the double bond equivalent would be n should be 8 plus 1 minus m. M is 10 divided by 2. So 8 plus 9 minus 5. So double bond equivalent would be 4. Like this. So if oxygen nitrogen is present, then there is some defined. Okay. So for the oxygen is that oxygen valence is 2 and nitrogen valence is 3. Right. So for the two valency system, the formula should be like this. No change. For the two valence system, like oxygen. For the oxygen, the formula is like this. Let's say we have NX, HNO, X. That time formula should be this. Now let's say we have nitrogen, HN, HM, NH. That time the formula would be N plus 1 minus M, here should be plus X divided by 2 for three-valent compound, trivalent compound. This is for nitrogen or trivalent compound. Okay. And if chlorine is there, I mean monovalent compound is, this is for divalent. For divalent, you have to do nothing, just same formula. For the trivalent, you have to basically add something here. How many number of extra trivalent molecule is there? And for the monovalent, like chlorine, bromine, let's say CN, HM, Cl. This is for monovalent. So that time N plus X minus, sorry, here it should be minus, not the plus. For monovalent compound. So monovalent compound, you have to add that much compound. For divalent, you have to do nothing, and for the trivalent, you have to subtract. It's clear? So monovalent, you have to add. For divalent, do nothing, and for trivalent, you have to minus. Clear?
Yes, sir.
Okay. Then tell me what is the that compound is C6 H12 H12O6. What will be the double bond equivalent? So this is divalent compound under. So what is the divalent? So n plus 1 minus m by 2. So 6 plus 1 minus 12 by 2. So 6 plus 1 7 minus 6. So double bond should be DB means 1. 1, right? Clear? So
Yes, sir.
what is the significance of DB? So the significance of DB is that it can be one double bond. If DB is one, there are two possibilities is there. One can be double bond, one double bond, or one ring. These two possibilities there. One double bond should be there or one ring should be there. And if the DB is 2, say let's say one molecule has DB 2, that has many possibilities. It can be two double bond or two ring or one double bond, one ring. These three possibilities there. Either this or two ring or one double bond, one ring. If the DB. If the DB is 3, like this. Can you tell me what is the double bond equivalence of benzene ring?
4.
Yes. Because it has 3 double bond and 1 ring. So that means 4. 3 double bond, 1 ring. So 3 double bond plus 1. So 4. Now read the question again. So in this molecule, the molecule is showing only one peak in 1H NMR and also one peak in 13C. What it means? Only one peak, both case. That means molecule is highly symmetric. It is clear or not? If the
Yes, sir.
molecule, yes, because in the benzene ring proton, all the protons shows only one peak because that is symmetric. So here also it is also symmetric. So now tell me, it should be double bond or ring? Based on the because DB is one in this case, we have already
Ring, sir.
ring. So which type of ring? Now try to answer.
Heterocyclic ring.
So try to draw. I mean how what is the name of this ring? It is known compound, well known compound. And can you tell me what is the 13C value is showing 70.7? What is the meaning of that? That means the carbon is attached with some electronegative atom. I mean CO bond should be there. That's why the carbon 13C is 70.7. And the hydrogen is also little bit downfield. I mean 3.69. That also means that there should be some CH bond O. Okay, before that I am trying to say something. Let's say if you have CH3 group, the value should be 0.9. If you have CH2 group, the value should be 1.4. If you have CH group, the value should be 1.7. Can you explain the observation, the delta value? If the hydrogen is less, then the value is high and downfield. If the hydrogen is high, then the value is low field. Let's explain this. For the 1H NMR, this is for 1H. Can you explain why this is like this? Why the number of hydrogen when decreases, the value of delta value is increases? Can you tell me what is more electronegative, carbon or hydrogen?
Repeat again, sir.
Which is more electronegative, carbon or hydrogen?
Carbon.
Carbon, right? So in the CH3, what is the CH3? So here is one carbon. In the CH2, here one carbon, here one carbon. In the H only, one carbon, one carbon, one carbon. So 3 carbon is basically taking the electron, right? Here two carbon is taking the electron. Here one carbon. So that's why this is more desilted. More desilted means that the delta value is high, means the electron is around the nucleus is less. That is clear, na? I mean the electron is less here. Electron around that particular hydrogen, is less. That's why that we call the desilted, or we say downfield. Different term is used. So downfield or desilted means less electron around the nucleus. That means desilted or downfield or delta should be high. Delta should be high. In exam, it can be framed in three different ways. Desilted, downfield, or delta is high means that the electron particular about that nucleus is less. Okay, it is clear I think now. Because it has 3 carbons, so as the carbon is more electronegative, so the electron around this that particular hydrogen should be less compared to these two. Same region here, so that's why it is more desilted. Okay, so if you check the Claden book, there is one table. That table summarizes if let's say CH3CO is there. So you know that CH3 value should be 0.9 from this. So 0.9, and in the Claden book there is one just small table. Take that if the carbonyl group is there, you should add 1. So the value should be 1.99 approximate. And this type of table help you to calculate many things actually. Let's say if you have CH3 or COCH3 like this group has FH around 3. So that time this is 0.9 plus 3. So it should be 3.99. So you can easily differentiate whether it is attached with keto or it is attached with like oxygen with keto group. And if the normal oxygen is also there, na, that time also it like ether bond. That time, so this value should be 0.9, and this ether group has a around the value is 1.5. So around 2.4. Okay. Sorry, ether has a value is around 1. Around 1. So it should be 1.9. Okay. And now this CH2 should be what value? So this CH2 is 1.4. 1.4 plus this ether is there, that value is 1. So that will be around 2.4. Clear?
Yes, sir.
So here's the Claren book, and that table you practice on different 2-3 molecules. So you can get a rough idea. So you have to remember not too many groups, especially ester, keto, like halogen. If you know around 3-4 group value, I think your life will be easy. So again come to the question. So the value is around 3.69. Okay. So that means, and the dB is 1 and the 13C value is 70.7. So now I put about 13C. So okay. If normal CH2, CH3, normal, if is there, then in the 13C, the value should be 0 to 50. If CH3 10 to 20, 20 to 30, rough value I am saying. This is 30 to 45. Normal. It is not value with electron withdrawing group. If we attach with like electron withdrawing group like halogen, then its value should be 50 to 80. If one double bond is there or benzene ring is there, its value should be 122, around 155 for double bond region. Okay. And for 162 to 220, this is for keto group. Keto A star. Okay. This is a particular group. So in our compound, the value is around this. So that means our compounds must be attached some electron withdrawing group, like CO bond should be there because oxygen is only there. Okay. So now solve the question. So the value is C12H24O6. So and so only one peak in 1H NMR and delta is equal to 3.69. And the 13C NMR shows the 70.7, the reduced structure. So you get one information that compound should be symmetric because the DB is 1, so that must be cyclic. So you have to place all the carbon, hydrogen and the oxygen in such a way that all the groups should be symmetric. And from the 1H NMR, you also get some idea that it must attach with some electron withdrawing group. I mean, O should be there. And from the 13C also you get some idea. So can you draw the structure now? Okay. C12 C12 is 24 over 6. 12 plus 1 minus 24 by 2. 113 minus 12. So double bond equivalent is 1. So double bond or one ring. So double bond is there, then the symmetry will not come. So it must be should be ring. And we know that from the 13C, CO bond should be there and CHO bond should be there. So how can and the molecule should be highly symmetric. So for that, you always see oxygen 6, carbon 12. Means how can we arrange 12 carbon and 1 oxygen? So 12 carbon and 1 oxygen, how can we symmetrically place? So 2 carbon, 1 oxygen. If we place like this, 2 carbon, 1 oxygen, 2 carbon, 1, 2, 3, 1 oxygen, 2 carbon, 1 oxygen, and 2 carbon. How many oxygen? 1 oxygen, 2 oxygen, 3 oxygen, 4 oxygen, 5 oxygen. Okay, so the skeleton should be like this: 2 carbon, 1 oxygen, and now place the hydrogen here. Okay, the actual molecule should be clear because it has one symmetry pointers. Due to that, all the rotation is possible. You can plus one sigma plane here. You can rotate this molecule. Many sigma planes there. See? So the structure is 18 round 6. Clear it is, I hope?
Yes, sir.
Okay. this type of symmetry molecule is very difficult to find in real life. I mean, in exam or in in MCQ it is fine, I think, but you need lot of depth to find this type of symmetry molecule. Okay, is there any question? So read Clarion one time this to how to calculate the chemical shift, so you can get a real good idea how to solve. At least you can see that you can tell anything like what will be the chemical shift, exact, not exact, around chemical shift. So that will help in exam a lot. So if there is no question, then we can stop today. Okay, thank you.
Thank you, sir.
Thank you. Is there any question?
Sir, please explain the 4 DEB for benzene.
Okay, okay, that's 1 minute. So for double bond, one count, and for ring, one count. Okay. So in the benzene, how many double bond is there? Tell me.
3, sir.
And how many ring is there?
1, sir.
One. Okay, tell me now. For this molecule, what will be the DB? So 3 and 4. 4 double bond, right? And one ring, right? So the DB should be 5. Now tell me this molecule. For this molecule, what will be the DB? How many ring is there?
2 rings.
2 rings. Okay, then DB should be 2. Now this molecule, 2 rings plus 1 double bond. So DB should be
3, sir.
3. So in exam, if your DB calculate around 4 or 5 or higher than that, there must be one benzene-like system. Benzene, or it may be pyridine-like system. Clear? Normally, not always. If your DB comes around 4 to 5, then you think that there may be on benzene ring, then you go to the NMR and check, is there any value around 6.8 to 8 ppm? Check that. If it's there, then there must be benzene ring. Okay, clear?
Yes, sir. Thank you, sir.
Huh. Okay, thank you. Is any other question?
No, sir.
Okay, thank you.